Justin Miller, I'm called Physics here, and we are going to do a nice little problem with some refraction. So we're going to take some different substances, kind of stack them on top of each other and ask a couple questions about the path of the light ray and maybe something with some critical angle. Sound good? Heck yeah, it does. Sounds awesome. You ready for this? 1, 2, 3. Okay, so that's what we've got. We've got ourselves 3 materials that are stacked. We've got a zircon, we've got some water, and we've got some air. Each of these has its own index of refraction. We'll say n sub z, 1.92, n sub h, we'll say is 1.33. A lot of times you use 1.333 for this, 1.33. And for air, we're always going to say n sub air is equal to 1.00. We just assume that air has a really small index of refraction. That the speed of light in air is just about the vacuum speed. Just about unity for the index of refraction. So there we go. So we've got these 3 layers all parallel to one another. Then we're going to take ourselves a nice little light ray, and we're going to say that that ray is incident upon the zircon-water interface at an angle of 25 degrees with respect to the normal of that interfacial boundary. So we can draw in a little boundary here. And we're going to take ourselves a light ray that has an angle of approximately 25 degrees. So we'll call this theta sub 1. Theta sub 1 is equal to 25 degrees. And what do we want to know? Ultimately, we want to know what angle does this ray exit back out into the air, if it even does. So what we want to do is sort of draw in some expectations here, and then we can go through and quantify some stuff out. So we are going now from zircon into water. Here's the interface boundaries normal between those 2 materials, right like that. And the question is, for drawing this out, is the light ray going to bend inward towards the normal or outward away from the normal as it enters into the water? And what you have to look at? You have to look at the indices of refraction. If we go from a higher index of refraction into a lower index of refraction, the light ray will bend outward because the light's speeding up, zips out. So to some degree, this light ray will bend outwards, maybe exaggerated, but nonetheless travels out like that, and we will have this theta 2 right here. Regarding theta 1 and theta 2 of that interface boundary. And then what happens? Well, now we've got this, striking this interface boundary between the water and the air. What's it going to do now? Well, again, we're going from a higher index of refraction into a lower index of refraction, so it should bend outward again. So that's exactly what it's going to do to some degree. Maybe not as drastic, but there's a straight path. Maybe you go something like this. Boom, bends a little bit. There we go. Well, I don't want to call this theta 1 again and theta 2 because we've already used those here. So let's call this theta 3 and let's call this theta 4. Because really, the subscripts are just for keeping track of things. So, what do we have with this? The question is, part A, ultimately, what is theta 4? What angle relative to the normal of the interface boundary between the water and air does the ray exit out into air? So in order to figure that out, we're going to kind of go through the process here and just do just that. All right. So we've got refraction occurring here, and we've got refraction occurring here. So let's break this up and say right there, here, we've got ourselves an n1 times the sine of theta 1 is equal to an n2 times the sine of theta 2. Snell's law applied to this interface boundary. We're going from n1 into n2, or n sub z into n sub h, and we've got a theta 1 and a theta 2. So if we wanted to sort of augment this a little bit, this really goes from n1 is equal to n sub z n sub z times the sine of theta 1 is equal to n sub h times the sine of theta 2. So this is how I want to correlate things. What we're going from and what we're going into. From, into, from, into. Fantastic. Well then over here, we've got ourselves an n, you could say n1, I don't want to call it n1 again though, so I go ahead and call it like n2, this is what we're calling n2, and then n3. And ultimately, it's easier at this point just to say that this is n sub h, we're going from water into air, so we've got ourselves n sub h times the sine of theta sub 3, that is the angle with respect to the interface boundary. Interface boundary is normal. And h sine theta 3 is equal to n sub air times the sine of theta 4. There we go. So, kind of got this spelled out at very least, and now it's about being able to quantify this all down. All right, so what can we do? Well, we can go ahead and start figuring out what theta 2 is from this, right? So we could move stuff around, isolate theta 2. So we're going to divide both sides by n sub h, and then take the arc sine of both sides, and get ourselves that theta 2 is equal to the arc sine of n sub z over n sub h times the sine of theta 1. Which gives us that theta 2 is equal to arc sine of 1.92 divided by 1.33 times the sine of 25 degrees, which gives us theta 2 is equal to, be careful here, we're using angles in degrees, right? Calculators in degrees, so if it's not in degrees, change it to degrees. Mine is in degrees, so we're good. We've got the arc sine 1.92 divided by 1.33 multiplied by the sine of 25. Gives us about 37.596. Whew, that sounds nice. 37.596 degrees. 37.596 degrees. Which is greater than 25 degrees, again, because it's bent away from the normal. So that all makes sense. Great. Well, now we want to take this and see if we can figure out what theta 4 is. So I could go ahead and solve this out for theta 4, right? Isolate theta 4 is going to be equal to the arc sine of nh over na times the sine of theta 3. All right, so what's theta 3? Well, this is where we have to be a little bit careful, but in this case it ends up being pretty simplistic to figure out. If we want to get what theta 3 is, what do? Well, if we notice that we've basically got this. We've got this, something like this. Here's our theta 2 right there. Here's our theta 3. They have to be equal angles, right? They have to be because the normals are aligned with one another. This is 90 degrees, that's 90 degrees. These two lines are parallel with one another. Theta 2 is equal to theta 3 here. Now, if one of them was tilted down, that wouldn't be the case. And that's where you have to be really careful of figuring out the correlation between a theta 2 and a theta 3, or a theta and the next theta. But because the surfaces are parallel to one another, we have vertical angle sort of correlations here. And we got theta 2 is equal to theta 3. So theta 3 is equal to theta 2, which is that right there. So we can go ahead and get what theta 4 is. Theta 4 is indeed equal to the arc sine of n sub h, which is 1.33, divided by n sub air, which is 1, times the sine of 37.596 degrees, gives us, should it be bigger than 37.596? The answer is yeah, because it bends away from the normal. It increases by a single amount. And 3 times the sine of the answer, 596 is what I have written here. 54.236, we'll call it. 54.236 6 degrees. There we go. We've got the in-between and the outcome. Pretty cool, right? All right, so then we transit on over to a part B. Part B asks something very specific. What does theta 1 have to be such that theta 4 is 90 degrees? Or, worded in the actual question, what does the angle of incidence at the zircon water interface have to be such that the ray arrives at the critical angle at the water-air interface? So we want this theta 3 now to be the critical angle between these two materials. There's a particular theta 1 that can make that be the case. So let's draw this out. That will be helpful in us keeping track of things. Got these two surfaces again. And ultimately right there, with that 25 degrees, it does exit back into air. So we should note that if we start increasing theta 1, we'll start increasing theta 2, which increases theta 3, which will increase theta 4 as well, but theta 4 is already bigger than everything else, so eventually theta 4 goes to 90 degrees. That's what we want. We want it to go to 90 degrees. So this is what we ultimately are after here. We are after this. I'm kind of working backwards a little bit here. We've got theta 4 is equal to 90 degrees here, which means that theta 3 has to be equivalent to theta sub c. Theta 3 is equal to theta sub c. A critical angle. And we already know we've got ourselves a theta 2, which is equivalent to theta 3. We just put in a theta 2 here. There's a theta 2. And it was a little bit sloppily done, but clean that up a little bit. And then this is a little bit steeper. This isn't scaled out properly by any means, but something like this. Here is a theta 1 equals a what in order to produce that. So it comes in, bends outward, comes in, bends outward such that that last bending is at 90 degrees with respect to the interface boundary. It's normal. All right, so how are we going to do this? We're going to work backwards. We're going to say, hey, we know what theta 4 is. What does theta 3 have to be? If we can figure out what theta 3 is, what it needs to be, that's equal to theta 2. And if we know what theta 2 is, then we can get theta 1. Pretty easy, right? Whoa, whoa. Settle down, settle down. We got an n sub c, an n sub h, and an n sub air still. Got those three surfaces there. So we come over to this one first. And we've got ourselves n sub h times the sine of theta sub c is equal to n sub air times the sine of a 90 degrees. Yeah, 90 degrees. There we go. So what's the sine of 90? Sine of 90 is just equal to 1. That's great. So that allows us to define theta sub c really easy, right? We've got that theta sub c is going to be the arc sine of n sub air divided by n sub h. That's how we're always going to end up defining theta c's, because we always have that this angle here is 90 degrees, sine of 90 is equal to 1. You're always going to end up with something similar here. Notice that this is only defined if n air, or the top n, the numerator, is less than the denominator. Because this number here has to be less than 1, less than or equal to 1 for theta to be a defined quantity. So, it's a nice little expression there. Anyways, that allows us to find what theta sub c is. So let's just go ahead and say theta sub c then is the arc sine of 1 divided by 1.33. Arc sine 1 divided by 1.33 gives us 48.753. 48.753 degrees. there's the critical angle between the water-air interface. So we're after, what is theta 1? Well, that's what theta 3 was equal to, and this also has to be equal to theta 2, because again, these two surface boundaries are parallel to one another. Theta 3 and theta 2 are equal, so then you can come on over here and say that we've got an n sub z times the sine of theta 1 is equal to n sub h times the sine of theta 2. We want to solve this out for theta 1, given that we know what theta 2 is, equivalent to theta sub c, and we've got ourselves that theta 1 is equal to the arc sine of n sub h divided by n sub z times the sine of theta 2. Arc sine of n sub h divided by n sub z times the sine of theta 2, which gives us theta 1 is equal to, oh, that's 1.33, that's 1.92, and theta 2 is our 48.753 degrees. And we've got the arc sine of 1.33 divided by 1.92 times the sine of that. 31.388 degrees. So, if we have this path being 31.388 degrees, we'll have reached this boundary at the critical angle and get a 90-degree refracted ray. If this theta 1 exceeds that 31.388 degrees, we will exceed the critical angle here, and then we'll start to get internal reflection regarding the surface. We'll just get light reflects off of it. And that's it. And then it would probably enter this, and then refract back out. Not probably, it would. Anyways, that's it. Cool little problem. Utilizing some critical angles and just some general refraction. And that's that. Alrighty? Alrighty. Take care, be well, until next.